Hello everyone, I'm Emily Sun from the Department of Physics and Astronomy at Northwestern University. I'm glad to talk about my research here today. So we use computers and internet on a daily basis. There are two things we consider. One is the computation speed, and one is the communication security. So engineers have been trying hard to put more and more circuitries on a single chip to increase the computation speed. But it is getting harder and harder, and it's almost reaching its limit. So instead of pushing ourselves to the limit, we can find other ways to make the improvement. That is to take the advantage of quantum mechanics and take the leap to do quantum communication, which is more secure, and to do quantum computation, which is much more faster. So it is actually the different way of representing information that makes a quantum computer more powerful. So in a classical computer, we use binary digits, bits, and the value of each bit can be 0 or 1, like the quarter shown here. It can be heads up or tail up. However, in a quantum computer, we use quantum bits, a qubit, and the value of a qubit can be 0 and 1 simultaneously. Just like the quarter, rotating quarter, you cannot tell it is head or tail. And based on this quantum way of representing information, protocols and more efficient algorithms have been proposed, saying that quantum computer is more powerful. But those are just theories. As an experimentalist, I want to make a quantum computer on the table. So here's the first question. What to use to carry the information in a quantum computer? So in a classical computer, we use electrons to send the information. And in a quantum computer, photon is one preferred candidate to finish this task. And what is a photon? You can understand it as a particle in the light. So here is the advantages for using photons to build to carry the information. The first is a photon can help realize the quantum way of representing information. The second one is photons can be easily distributed through the telecommunication network, which we already have. And the third one is doing optical communication. We can actually have higher bandwidth. And what it means is that instead of using one railway to send out products, you can have these parallel railways, and you can send products more efficiently. So here we have the information carrier. The next question is, where are you sending them? So in a classical computer, people use materials with different electrical properties to build various devices. And in a quantum computer using photons, all optical devices will be needed. And using nonlinear media to build these all optical devices is one option. So nonlinear media is one special kind of material that exists in the nature. And within such kind of material, intense laser light can have interaction. Just like the picture shown here, with a red laser light coming in, you can have green laser coming out. And one great example would be the laser pointer. So in order to have a green laser pointer, you generate red light inside. And use a small piece of nonlinear medium, you can turn it into green. So the research I've been doing is to try to build a switch using this nonlinear media, which helps the quantum computing. So just like the light switch that turns light on and off, there are a lot of switches in a classical computer that turns the value of a bit from 0 to 1 or from 1 to 0 according to the computation order you send to the computer. And in a quantum computer, we also need such switches, and we start with the fifth switch. So in our case, a signal comes in, and when a switch is on, the signal exits and stays the same. And when the switch is off, the signal is flipped, and you have a different state. But this task is very challenging. The first challenge is that a quantum computer works with single photon, and single photon is very weak light. A 40 watts bulb sends out billions of photons per second. So using weak light to control weak light is very challenging. And our solution would be to introduce optical whispering gallery. So here's a picture for a whispering gallery at Beijing. If you whisper at one point on the side, the sound wave will circulate in the gallery, and then you can hear the sound clearly at other point. So in optics, we can introduce a disk that behaves like an optical whispering gallery that confines light inside and increase the power of the light. So the second challenge would be the signal is your information. You don't want to disturb it. So we will need a noiseless way of control the signal. So our solution is to use the quantum Zeno effect. In a simple sentence to explain it is that a washed pot never boils. And in our case, the story would be the state of a washed signal photon doesn't evolve, and it happens when the switch is on. So here is our device. We have a disk that is our optical whispering gallery, and the prism is used to couple the light into the disk. And the signal photon circulates in the disk and comes out at a flip state, that is the switch on. And in another case, we send a pump photon to turn the switch on. And the pump photon will couple into the disk and watch the incoming of the signal photon. The signal photon will actually not entering the disk and exit with the same state. That is the switch on case. And our research shows that under certain circumstances, over 95% control of the signal can be achieved. So let me wrap up. We have built a phase switch that works at single photon level, and this can be a basic computation unit for a quantum computer. Although there are still a lot of problems need to be fixed, but in the future with a quantum computer, you can do more efficient data searching, or you can simulate more complicated systems, which helps the advance of science in almost any field, and you can even have perfectly secure communication. And I want to make that happen. Thank you.